Yeah, so now we're going to look at continuous control, controlled by regulators or controllers or whatever you call them, PID controllers. Again, we're just going to look at the compendium here. And what we're going to look at now is continuous control. Control loops or controller loops. Again, we look here a controller. We have a continuous controller of some kind of type, which is again a class or function block with code and data. We have got parameters to tune the controller. We have feedback from the process value. So this is a closed loop, a single closed loop, single loop controller. It has a control value, a process value, and it tries to keep this process value within acceptable limits. And we have an operator here that can maybe set the set point for the controller, do manual control, set the control value directly to the process, and so on. So this continuous loop controller instrumentation. So it says here, says a little about this, the requirements here. Modern field buses that we usually use, they are stable enough and have quality codes that your values are intact. So they are feasible to use as instrumentation, smart instruments or whatever. And then if not, use a legacy 4 till 20 milliamps signal, because here you can detect errors on the signal, short circuit and open circuit and so on, in this type of signal. Then it's the output, and here you could use an analog output, an actuator with a validation signal. So the actuator electronic does not do anything to the control valve. If maybe it should stay put if the automation device fails and loses the validation signal. Of course, with a smart actuator here, he is communicating with the automation device, so he knows, do I get some new values or something? Is this automation device alive? And if not, the actuator device can do whatever it should do. Maybe you can parameterize the actuator electronics to close the valve or open the valve on a fault or whatever. Again, 4 till 20 milliamps can be used if you have to use legacy signals. Yeah, and you can also use digital outputs to the control valve. Then they also often frequency modulated or pulse width modulation. The latter is most often the case. So you can open and close the valve, and if your device fails, the valve stays put. Of course, this actuator could be a heater. So we turn on a heater, turn off a heater. The longer we turn the heater on, the more we heat, and so on with pulse width modulation. So we don't have an analog output to control our actuator. We actually have to use a digital output. But then, of course, only with one digital output. And again, the process value can be an ultrasonic level sensor or some other. So that is continuous control. And what we're going to look into now here, there are various types of controllers, but we are going to look into, let's say, continuous controller functions here. I'm just going to walk through that. A PID controller with a programmable device or automation device. They have pre-programmed function blocks when we look at PLCs that implement a PID algorithm. But maybe you have to write it yourself. So the function for a continuous controller, we have talked a little about it. We have a controller, it has a set point, what it should achieve for value. We have a process value or control value. SP, PV, CV, they often abbreviate that. So that's a continuous controller. Here again is the level control example. It's not in this. So one controller it's a PID controller, a proportional integral derivative controller. So it has a control effort or control value that's proportional to the has a proportional value, an integral value, or a derivative value of some type of measurement. So it is a control error normally. And here is the algorithm. So it's proportional to the error. It's also proportional to the integral of the error. but then divided by an integration time. And it's also proportional to the derivative of the error multiplied by a derivation time, and always multiplied with this proportional gain. So this is an ideal PID controller algorithm. And it also has a bias, often called also a feed-forward value. So it's a bias. Let's say the YOT is a 0 to 100%, which is no control effort to full control effort, full flow or whatever, full heating or what you have. And the bias can, for instance, be 50%. So 50% is your base load. 50% is what we need to keep the room comfortably hot. And if it's colder out, we have to increase a little and do a little control here. Whatever, or a feed-forward value. Yes, a PID algorithm, if you look at it, if it's only a P controller, PID, but it's only a P controller, we have a static error, which is nullified by the integral party. There's another one too, which is called an incremental algorithm. What we do, we just differentiate the algorithm we have up here just to get rid of the bias. We can get rid of the bias, but then you don't have a bias or feed-forward value. So if you need that, you need this algorithm. So you might need both. Okay, and then the output itself, you just have to integrate this one with respect to type again. So this algorithm uses Euler's first order integration method. You can use second order and so on, or other integration method, but usually use first order because it's good enough. The controller sampling is fast enough, so it's you don't get big jumps or jumps. You get a straight line here for the derivative and things like that, and then it's exact. Whatever, but from the figure we have approximation for the derivative, second derivative, and for the integration. The YOK minus 1 here is this area, or this value. It has nothing to do with an area, but this control effort. And then we just add this one as we go on when we integrate here. And then we can substitute it into the absolute algorithm and the incremental algorithm, and so on. And what we have to do is to implement this in our function block, in our automation device or PLC, or whatever you use to do control here, and so on. And that's a relatively easy task. It's not that hard to do that. And again here, what we're going to do next is this. It has to do with tuning of this PID controller. And the PID controller has to be tuned. You have to adjust these KP, TI, and TD. Proportional gain, integration time, and differentiation time. They have to be tuned. And next we're going to look into some tuning methods for controllers. Yeah. So here we looked into continuous control and especially a PID controller and two algorithms. An ideal algorithm with two variants. It's an absolute one or an incremental algorithm. And then we looked at, let's say, the difference equations that you have to implement in, for instance, a PLC to program a controller like this. If you have to do it yourself, to make a do-it-yourself PID controller.